Hey there, math folks. Got to get the mute turned off before I start talking here. Hope you're all doing well. Back here with another video. I don't know how quick this one's going to be. I have a few things I want to walk through with you, and it does involve several proofs, so it could take a little bit of time. So I don't think I'm going to spend too much time elaborating here to begin with, but what we're going to see, folks, in this next video is just looking at some common derivative rules, right? Some of what we might think of as our fundamental set of rules for differentiation. We're going to look at using that derivative definition that we explored in our last video and applying it in some generic situations that are going to give us, in a sense, a set of rules, some fundamental rules that are going to allow us to differentiate up through we might think of as the case for polynomial functions. We're going to see a lot of use with these rules is in the use of finding the derivatives of polynomials. All right, but let me get into this. Like I said, there's quite a bit here, so let's not waste time. We are going to be looking at common derivative rules. We are going to be using that definition of the derivative to present these rules, right? To develop these rules. The first rule we're going to consider is what's called the constant rule. And this is what I mean by using the definition. Consider differentiating a constant function, right? A function f of x equal to c, where we can think of the value c being any constant value. Well, we know from the definition for the derivative of this any function, the derivative of f is the limit as h approaches 0 for f of x plus h minus f of x all divided by h. Where in the case of the constant function f of x equal to c, f of x plus h is also just c in value because it is constant. There's no variable x to replace with x plus h. So when we set up this limit definition, right, that we understand from the definition of the derivative function, we set up a value given by the limit as h approaches 0 for the quantity c minus c divided by h, because f of x plus h is equivalent to c, and f of x is equivalent to c in value. Well, c minus c we can note is equivalent to 0. So in the numerator we have the limit as h approaches 0 for 0 divided by h, which is really just the limit as h approaches 0 for 0. And the limit of any constant is the constant itself. So all this just equals the value of 0. And what we've just shown using this definition of the derivative function, that if I have any constant function, its derivative will always equal the value of 0. The derivative of any constant is equal to 0. The derivative of 5 is equal to 0. The derivative of negative 3.1786 is equal to 0. The derivative of the square root of 2 is equal to 0, right? The derivative of any constant is equal to 0. Right? This is known as the derivative of a constant theorem. Right? This is our first fundamental rule for finding derivatives. Right? If you have a constant function, now if you think about the graph of a constant function, it is a horizontal graph. The slope of the line tangent to a horizontal graph is always going to be 0. So this calculation makes perfect sense in that interpretation. And for any constant, the derivative with respect to x will always equal 0 for that constant. That's what the derivative of a constant function is saying. All right? So that's what we're doing with these rules, is we're taking a generic form of a function, like we did in this case for the constant function, applying a definition to the form to develop a rule. Right? A rule in the form of one of these theorems, a theory that we've proven true with the definition. All right. Let's look at some more rules on this list. I think there's three more we got to look at least in this set, right? What follows, another common rule is what's called the power function rule, the derivative of a power function. And it's a little bit more involved in its proof. However, the rule itself is not too heavy to apply, right? It says, consider having the power function f of x equals x to the nth power. N can be any real number except the one thing that it cannot be is the value of 0. Right? It's not going to be the case for n to the 0 power. What is n to the 0 power? Well, that'd be x to the 0 power, I should say. Anything to the 0 power is equal to 1, which would be a constant function at that point. And that's not what we're looking at. We're looking at power functions, powers of x, not constant functions. We're looking at functions that either look like parabolas that open up or down, or we're looking at functions that look like the cube function, increasing or decreasing. Right? Now, what the power function rule says for derivatives is that if you take the derivative of x to the nth power, that becomes n times x to the power of n minus 1. What we often say when finding the derivative of x to the nth power is that the n is moved out in front as a constant multiple times our function x, where then that x is raised to a power that's 1 less than the value of n. It would be reduced by 1 to the n minus 1 power. This is called the power function rule. Now, we've already seen it in action when we were looking back at f of x equals x squared. When we apply the power function rule here, that 2 becomes a constant multiple out in front times what's now going to be a power of x, where we take 2 minus 1, which is 1 in value. And we end up with 2 times x to the first power. Right? That's following the power function rule. If we had x to the third power, it'd be 3x squared. If we had x to the negative second power, well, it would decrease by 1, so it would drop to negative 3. It would be x to the negative third power, but that negative 2, that negative second power, would become the constant multiple. It would be negative 2x to the negative third power. That would be the power rule applied to x to the negative second power. Right? It's all about what is the power. The power will become the constant multiple in front, and then the power on x will reduce itself by 1. There is some proof of this rule. If we get into the proof, here's the proof. If we let f of x equals x to the nth, and we're going to run into c sub I in this statement. C sub I just be some arbitrary constant for what's going to be an ith term. From the definition of the derivative, f prime of x, which equals the derivative with respect to x for x to the nth power, all of this is equal to the limit as h approaches 0 for x plus h to the nth power, right? Minus x sub n, all divided by h. Where since f of x sub n, or f of x is x sub n to the nth power, x plus h to the nth power is going to be f of x plus h. And if we expand its quantity outward, we've done this before. When we were looking at, I think in the previous set of notes, we had an x plus 2 to the third power. Here we have an x plus h to the nth power. This will undergo what we call a binomial expansion. And through its binomial expansion, x plus h to the nth power can be written as this generic polynomial form. It starts off as x sub n plus n times x to the n minus 1 times h plus c, where c sub 3 is the constant coefficient for the third term, as we've defined above as c sub I, for x to the n minus 2 times h squared, plus this pattern holding all the way down until the very last term, will naturally turn into h to the nth power. Right? This is the pattern we follow when we look at, if I was to expand on this generically, right? If we were to look at something like x plus 2 to the, well, maybe I should say it this way, x plus h to the second power, this would be x squared plus 2xh plus h squared, which would be a description of the above pattern following for the nth power of x plus h. If I was interested in x plus h to the third, let's get that third in the right spot, to the third power, I know from doing several binomial expansions through my time that this is equivalent to x cubed plus 3x squared h plus 3xh squared plus the value of h cubed. Right? That would be x plus h cubed. And I can continue because I know how to follow this pattern. For x plus h raised to the fourth power, it would be x raised to the fourth power plus 5xh, well, careful there, 5x cubed times h plus 6x squared h squared plus 5x h cubed. Careful, those aren't 5s. Those should technically be 4s. My mistake. And then the last term would be plus h raised to the fourth power. Right? That would be the binomial expansion for x plus h to the fourth power. The above statement is a summary of that pattern to the nth power. Excuse me. Right? It does in general follow the above pattern, and we don't get into too much of the specifics because of the way how things are going to cancel in the next couple of steps. Right? We don't get into the specifics in this pattern of what are these constant values actually going to be. Right? What's important is to note that the first one in the second term will always be the value of n. And we can see that. This is 2, this is 3, this is 4. Where this 6 comes from, though, is not that important. What I will tell you is that it does come from the idea that 3 plus 3 in the coefficients from the statement above add together to give you 6. Where the coefficients actually develop from it is what we call the... What is that referred to as? That's referred to as Pascal's triangle. Go do some research on that, but that's where we would find those coefficients. They follow that pattern. Right? Now, if this is x plus h raised to the nth power, then if we take x sub n away from that statement, right? That's going to take x sub n away from the right-hand side and remove this very first term, leaving everything from the second term on down behind this value seen here on the right-hand side. Now, you will notice that every single one of those values that's left behind has a factor of h in the pattern all the way down. So we can divide out, when we divide out by h in the definition of the definite integral, what am I saying? When we divide by h by the definition of the derivative, we'll remove an h from each of those factors all the way down until the last one is h at n minus 1, but the first will actually eliminate its value of h. Right? Dividing out this first h will completely eliminate it from the very first term. And that's the h we're interested in being eliminated, because what we see now is if we apply the limit as h heads to 0 to the statement above, every term involving h will then become 0, right? That's what this limit is showing us, is that every term except for this very first term involves an h. And if h is going to head to 0 in the limit, then all of those terms, as substitution plays out, is going to turn into 0. Except for the very first term, it does not involve the value of h. And what is the very first term? Is it is going to be this term, n times x raised to the n minus 1 power. And that is where we end up with the proof, right, for the derivative with respect to x for the nth power, right, equaling n times an x raised to the n minus 1 power. Right? That above is proof of what's called our power rule of derivatives. Right? Take a quick break here. I'll be right back. All right, folks. So that was the proof of the derivative of a power function. That is probably the messiest of proofs that we're going to see here with this, at least this set of notes. Hopefully the others are a little cleaner. These do get a little messy when we start to think about just how do we think about x plus h to the nth power in general. And we do have a little bit of this dot, dot, dot going on in there, but we assume that we establish a pattern in there that behaves in a manner that essentially, as we see in the algebraic, is going to cancel itself out, right? When we come time to apply the limit to this, and through all the algebra that has canceled things away, when the limit applied, it doesn't really matter what I have in this dot, dot, dot here. It's going to involve a factor of h. And as h heads to 0, that term then is going to turn into 0. All right. So, there is a little bit of messiness in here, but it works out clean and nice in the end. All right. So we take note of that. Now we got two other proofs to look at. Let's see these. It's also called the constant multiple rule of derivatives. Let's bring this up. All right. Essentially, the constant multiple rule says that if you have the derivative for some constant times a functional behavior, then you can factor out that constant multiple from the derivative of that function. Right? The constant becomes a constant multiple of the derivative for that function if you're looking at the derivative for the constant multiple of that function. Right? That's called the constant multiple rule. For example, I give here, we might find dy dx, the derivative when y equals 5x squared. Right? Consider finding the derivative for this function where y equals 5x squared. Well, following the rules, that would be the derivative with respect to x for 5x squared. And that 5 is a constant multiple being multiplied by the square function. So I can take that 5 out of the derivative operator as a constant multiple and make it a constant multiple of the derivative for what is just the derivative of the power function x squared. And we know what the derivative of x squared is. That's 2x. So this simply becomes 2x times the quantity of 5. And 5 times 2 is 10, so this results in 10x. Right? That's application of the constant multiple rule. The derivative of 5x squared is 10x. If we had the derivative of 10x cubed, that would be 30x squared. Right? The 10 would come out in front as a constant multiple. The 3 from the x cubed would multiply by the 10 to give us the 30, and then the x would reduce by a power of 1. 30x squared is the derivative of 10x cubed. All right. Now a little bit of proof. What we do is we use the definition, but we start off by defining function g of x in the definition. Let me separate this. Here's the proof. Right? What we define g of x to be is the function formed by taking the constant multiple of function f. So when we're interested in finding the derivative for the constant multiple of a function, we're interested in finding the derivative of g of x, which is the derivative, well, by definition, is the limit as h heads to 0 for g of x plus h minus g of x all divided by h. Well, g of x plus h, if g of x is c times f of x, is just going to be c times f of x plus h. And g of x is just going to be c times f of x. So when I think about these two quantities here in the numerator, they both have a common factor of a constant multiple of c. And I can factor that constant multiple of c from both terms in the numerator and write it as the constant multiple times what's now going to be f of x plus h minus f of x divided by h when I factor the c out of each of these terms. And that c is a constant multiple inside the limit, where I know a constant multiple in a limit will also factor itself out of the limit. So bringing itself out of the limit, I have c times the limit as h heads to 0 for what is f of x plus h minus f of x divided by h. And that should look familiar, because that's what we define to be the value f prime of x. Right? The highlighted value there is f prime at x. So what do we have here? We have c times f prime of x, which is c times the derivative with respect to x. And thus, that is the derivative with respect to x for c times our function f of x in the end. Right? That is the derivative of that constant multiple of a function. That is its result. All right? Actually, I say that here, so I don't need to rewrite it here. All right? Thus, we have proof. All right? Now, we are going to put all these together in the end looking at a polynomial, folks. They're not too exciting individually quite yet. Where we really see them in action all at once is in a polynomial. So we're almost there. What we have to introduce for our fourth fundamental rule is what we call the derivative of a sum or difference rule. And here we have two functional descriptions, f and g. And we're interested in what's the derivative with respect to x for the sum or difference of those two functions. What's the derivative with respect to f of x plus or minus g of x? And what we see is that this derivative operator will distribute itself across this sum or difference, and it'll become the sum or difference, and that's what I probably should highlight here. This is sum or difference of the derivative for each of the individual functions. It's called the sum or difference rule. Do I give you an example here? I think I do. All right. Oh, no, I jump right into the proof to begin with. We'll see an example here in a minute where I put it all together. But if we think about the proof, the way the proof works here is we're going to talk about h of x being the sum of f and g at x, which is just f of x plus g of x. Well, h prime of x, which would be the derivative of that sum, would be the limit as little h heads to 0 for big H at x plus h minus big H at x all divided by h. Where if I think about what's big H at x plus h, it would be substituting x plus h into both of these values for x in that statement. That produces f of x plus h plus g at x plus h. And we'd be taking away f of or h of x, which was f of x plus g of x, and all that would be divided by h. where now, if I distribute this negative across these two terms in this quantity, I'll have minus f of x and minus g of x. If I then regroup the minus f and the minus g behind f of x plus h and g of x plus h respectively, I'll end up forming f of x plus h minus f of x for this first grouping. And I'd be able to add it to this second grouping of g of x plus h minus g of x. And let me highlight those as groups. Where each of those groups across this sum can be divided over this common difference of h. So I have the limit as f of x plus h minus f of x divided by h plus g of x plus h minus g of x divided by h, where how does this limit behave across this summation is it will distribute itself to each of those quantities. So when it distributes itself to this first group, it's going to form the limit as h heads to 0 for f of x plus h minus f of x divided by h. And when it distributes itself to the second group, g at x plus h minus g of x divided by h, those two groups should look familiar because they both define what is just the first derivatives, the derivative with respect to x for function f of x and function g of x respectively. Right? All this is equal to is just f prime of x plus g prime of x. And we have just shown our proof. Right? Thus, h prime of x, the derivative with respect to x for h of x, which is the derivative with respect to x for f of x plus g of x, is just f prime plus g prime of x, which is nothing more than the derivative with respect to x for f of x plus the derivative with respect to x for g of x, right? Implying that this derivative operator here in this statement will distribute itself across the sum to each of these individual functions f and g to form this statement seen here on the right-hand side. Right. These four fundamental rules all develop from using or applying the definition of the derivative to these generic situations. The generic case for a constant function, the generic case of a power function, the generic case of a constant multiple of a function, and now the generic cases for the sum and difference of functions, of two functions. And when applied, what we end up with is a list, a summary, a list of four fundamental rules. And here they are, just collectively, right? These are the four fundamental derivative rules that are presented in this section. You have the constant multiple rule, right? You have the power rule. Careful. This is the constant rule, power rule, constant multiple rule, and sum and difference rule. All right? Those are the four fundamental rules of derivatives, for the basics. These will allow you to find the derivative for any polynomial function. If we look at a polynomial, here's a polynomial. We might consider the polynomial f of x equals 4x cubed minus 7x squared plus 1/2 x minus 3. Right? The derivative f prime is going to be the derivative with respect to x for that polynomial. So how does this derivative behave with the above rules? Well, first thing is it's going to distribute itself to each of the terms across this sum and difference. Right? There's four terms in there. 4x cubed, 7x squared, 1/2 x, and 3. And it will distribute itself across each of those terms. Right? might look something like this. Now, when applied to each of these terms individually, right, in the first three cases, the first three cases involve a constant multiple times a function. The 4, the 7, and the 1/2 in these first three terms are all constant multiples times power functions of x. So they can be factored out of the derivative statement. So we do see that happen in the next step. We do see the 4 factored out of here, the 7 out of here, and the 1/2 out of here. But then for the last term, notice that's just the derivative with respect to x for a constant, and that's equal to 0. So in the end, that's just going to be subtracting 0 in that step. And now we just have the three derivatives involving these power functions, x cubed, x squared, and the derivative of just x. Now we've already seen x squared. X squared gives us 2x. Following the power function rule for x, well, that will bring the power 1 out in front times x to the 0. Reduce it by 1, becomes 0. So 1 times x is just x. Well, 1 times x to the 0. X to the 0 is 1. So 1 times 1 becomes 1. So this derivative here times 1/2 is just going to be 1. As we said, the derivative with respect to x squared is 2x. As for x cubed, well, the 3 moves to the front as a constant multiple, and you reduce it by a power of 1, so it becomes x squared. All right. It's going to be 4 times 3x squared minus 7 times 2x plus 1/2 times 1. The 3x squared from here, the 2x from here, and the value of 1 from this derivative here. Now when we simplify that, this will become 12x squared minus 14x plus 1/2. And that would be our derivative function. Right. Thus, f prime of x equals 12x squared minus 14x plus 1/2. And maybe we should highlight here, this is for f of x equal to 4x cubed minus 7x squared plus, what am I doing? 1/2 x minus 3. All right. F prime of x would be 12x squared minus 14x plus 1/2. And when you see the two side by side, right, you might actually start to see that that one could be found from the other pretty quickly. Right? Actually, you go back and forth once you see all the rules collectively. Right? But yeah, it shouldn't be terribly difficult to see where this might turn into 12x squared. And here we have minus 14x. And here we'd have plus 1/2. And then here would be minus 0. Right? When working with polynomials, you can develop that skill. And it should develop pretty quickly, right, with respect to their calculations. All right. But yeah, in summary, here are 4 fundamental rules, derivative rules, right, that will allow us to find the derivative for any polynomial function rather directly, right, just following the rules. As we had seen, they all develop from applying the definition of the definite integral to these 4 generic cases. The definition of the definite integral definitely does not want to be something we want to apply to perhaps this case alone. Applied here to this f of x, it could become really messy. But if we understand the rules above, we can see we can avoid that definition by just following the rules above. All right? So those are the first fundamental rules here, folks. What I'm going to come back to, let me come over here. fade that out. There's some more advanced rules. I haven't presented a product or a quotient rule yet. And you're going to want to be cautious with product and quotient. And then there's even a more advanced rule. Because we're talking about working with functions, we can also talk about a derivative for the case of a composite of two functions. All right? So we're going to get into that consideration also in some advanced rules. And then where we'll finish out is we'll look at some trigonometric, logarithmic, and exponential rules. All right, to kind of finish out the study on these generic rules. And then there's even more beyond that, folks, but that's where we're heading in the next couple of videos. So, but I will end this video there, and I will see you in the next one.